It's really great to be here. And I also want to acknowledge that this course is based on a lot of material by Cynthia Vincent, who is originally supposed to be given these, but she had a baby 2 weeks ago. Yeah. Okay. Yeah. So everyone is doing well. Yeah. So. Okay. So this Cynthia and I are friends and long-term collaborator. I've worked on topics adjacent to these, but I will now be talking about my own results. So I'll be talking about the title of the course is Log-concavity and Matroids. So I know that the name of the program is convexity and combinatorics in algebraic geometry. You know, if you take convexity and you like put it upside down, that is concavity. So, okay, so but we will not get to log-concavity today. Okay, we'll get to it tomorrow. Today I'm going to start with matrix. Okay, and we'll do obviously a bit of algebraic geometry, but not too much. You'll see more now to discuss. Yeah. Let's start with matrix. Yeah. So I'm not sure how much people know, just so that I have a sense, how many people have seen the definition of a matrix? Okay, like most of you, great. Yeah. So but there are some people who haven't seen, and I'll go over that. So for matrix is a tuple. There's a definition. So a matrix is matrix on a ground set. So for my course, we'll always stick to n element set, which will denote bracket n. So this is a set of numbers from 1 through n. It's a non-empty collection. It's a B, which is a non-empty collections of subsets of n. So matrix, maybe I should say a matrix is a tuple of the ground set together with collection that is a matrix. So, sorry, it's not grammatical. Right, so matrix consists of these data satisfying. It's really heavy. Maybe it doesn't move. It's broken. It's broken. I won't. This one, right. So satisfying the following. So satisfying. If I take two elements in B, so this is called a set of bases. So for matrix, what we're doing is trying to axiomatize the idea of an independence. So imagine, so later on we'll get to concrete examples, but you know these are maybe 1 to n. They are representing n vectors, and then this B is supposed to represent maximally independent collections of vectors among my chosen vectors, for example. Okay? So they will satisfy the following axiom. So for every A and B, and if you take satisfying for all collections, for all pairs A and B, and then if you take an element in A, not in B, there exists a B not in A, such that you can replace the letter A with letter B. So this is the definition. So maybe since I mentioned it, I'm just going to say that this was inspired by a collection of vector matrices, or also called representable matrices. Yeah. So if you let V1 through Vn to be in some vector space over some field, let's say that these vectors span F to the R, but it doesn't matter. You can always restrict yourself to a smaller subspace. And then you can let B to be subset of the vectors such that the vectors indexed, right? These are the indexes. So the vectors indexed by B They form a basis. Let's say that this is a spanning set for simplicity. Span is a basis of F3. So let's pause for a moment and check that it satisfies this axiom. Okay, if you have never seen this, especially. So if you have a collection of vectors and another collection of vectors, right? And if you have one that is not the other, you can kick one of this out and replace it. And how do you choose which one to replace with? Right, so if you have a collection of vectors and some collection of vector, I choose one here. And then how do I choose one on the other side? And that's too easy, or yeah, please.
Whichever one is not in the span.
Yeah, very good, thank you. So you look at the remaining, so you take the A and then you remove the letter A, and then you look at the remaining one and you look at the span, right? And then you choose something from B that is not in the span. There must be something not in the span because, you know, the B, they form a basis, right? So there must be something that is not in the hyperplane spanned by the remaining one, so you just replace with that. Okay, so, and then from the definition, we know from linear algebra that, you know, bases, all the bases are the same size in a vector space, right? So we want to also claim that all elements in the set of bases have the same cardinality. Good. Yeah, so again, let's pause for a moment and see if we believe that. Yeah, does anyone have a quick argument for why that's true? Someone else?
I just have a question about the definition.
Yes,
The
please.
A without the leg union little b, should that be in the?
Oh, sorry, this is privy, thank you. Oh,
Okay.
yeah, okay, thank you, that makes a difference, yeah.
I mean, this is not a mathematical argument, but it makes sense to say if we have any element in script UV and we can remove an element from it and then add an element and we have a different element in script UV and we can do that for any two of the elements in script UV, then it makes sense that they're probably the same size. We can get from any element to another by removing an element and then adding another.
Yeah, you're saying that if you take any two elements in script B and you can sort of like get them closer to each other by, right? So if you have two different sets, my A is bigger than my B, but then by this procedure, I could, you know, bring elements of B into A, replacing, right? So that they become closer and closer together, and eventually B is going to become a subset of A. And then if it is a strict subset, then this is going to fail. Okay, so yeah, thank you. Yeah, so that's a good intuition. All right, so yeah, so this is definition is really simple. This is the matrix, and it models different kinds of independences that shows up in mathematics, right? So another related thing to vector matrix is algebraic matrix. So for algebraic matrix, you take two fields, that's K and L, these are fields. And then I can take some elements, let's say A1 through AN in L. And I will say that let B be all the subsets of N, right, such that I indexed by I and B, they are algebraically independent over K. Algebraically independent over K, meaning that they do not satisfy a polynomial equation with coefficients in K. So it is a generalization of the vector matrix, because right here we're talking about linear relations, and here we're allowing polynomial equations, and again, they form a matrix. Let's see, now that we're talking about representable matrix. So you may ask, maybe all matrices come this way. But it's not the case that all matrices come this way, but there exists non-representable matrix. Yeah, so maybe the easiest examples, or maybe before I get to non-representable matrix, let me do some notations. So, and maybe easier kind of matrix are called uniform matrix. U or N, where I take my basis to be all R element subset of N. So this notation is all R element subsets of N, and it's easy to check that this is like the axioms, right? And then this is called a uniform matrix. And so, for example, U24 is not representable. So representability depends on your choice of field, right? Matrix can be representable over some field, but not the other. It's not representable over F2. Yeah, does anyone see that? So right here, we're looking at 4-element ground set. So to be representable, we're looking for 4 vectors in F2 squared, because this 2 means that every basis has 2 elements, right? So we're looking for 4 vectors in F2 squared. Every pair of them form a basis, right? Anyone see why that is not possible? Where?
Only 3 non-zero.
There are only 3 non-zero vectors, so you can have 4 vectors that pairwise form a basis, right? It's kind of a silly example, okay? But it is representable over any field larger than that, okay? So perhaps a more interesting example is something called a Fano matrix. So right here, when I draw things like this, so this is kind of like a projective case where my matrix elements are the dots. So this is this picture is supposed to encode, there is a matrix on 7 elements given by the dots. Okay? And then the lines here says that the affine independence. Or maybe another way to think about this is if you have an origin somewhere behind the blackboard, and then I'm pointing 7 vectors. Nice. And then the line here means that they are on a hyperplane. That means that they do not form a basis. Okay, so this is a rank 3 matrix on 7 elements. And these lines denotes the one that are not bases, including this curvy one. These are supposed to be not bases. Okay, so it turns out that this encodes projective space F2 cube without 0. They have this kind of linear independence. So it is representable over F2, but it is not representable over any field of characteristic not equal to 2. So this is called Fano matrix. And similarly, something called is a non-Fano matrix. This is these 7 points without this curvy line. So this is these are 7 vectors in something like, all the if you take the 0, 1 cube, right? So all the 0, 1 vectors, right? There are 8 of them. You throw away the origin, there are 7 left. Okay, those 7 will satisfy this kind of linear dependencies, and over any field other than characteristic 2. Right, so this is representable. This is non-Fano, is representable over field of characteristic not 2, but it is not representable over characteristic 2. And I'll also show you another example, but it's not representable over any field. It's something called non-purpose matrix. So that is set up to break the purpose theorem in projective geometry, where you have 3 points here and 3 points here like this. And then I'm going to add 3 extra points by doing this. Yeah. So purpose theorem says that these 3 extra points that you get has to be collinear. Yeah.
I wonder, it seems you might have started a few minutes early and some of the students missed the beginning. I was wondering if you could recap what you went through in the beginning before going too much further.
Okay, sure. Yeah. So I started with definition of matrix. So yeah, so I'm not going to get to the log-concavity today, right? So definition of matrix is a axiomatization of the idea of independence in mathematics. So we start out with yeah. So you can look at vectors in a vector space and linear independence, or like algebraic independence over a field, meaning whether these elements satisfy polynomial equations, right? So we can check that they satisfy this nice axioms where you take two elements, two bases. So a matrix is a ground set together with a collection of elements called bases. If you take two bases, you can do this thing called base exchange. You can take one element out and then replace it with something else in another basis. So that is the definition. So we're going through different examples of matrix, how matrix show up. So mostly I'm focusing on the vector matrix at the moment. So they come from linear independence among the vectors, right? And then this is what is meant to show is that not every matrix come from vectors. Not every matrix come from vectors, right? So right here, it also depends on the choice of the ground field. I'm getting to this example where so I look at this matrix right here, right? So right here again, the lines means that these are not independent, right? So I'm looking at matrix on 9 elements, right? So lines means the 3 element collection, right? 3 subsets that are not independent, and I do not put a line through the middle 3 points, right? So that means that I am declaring them to be independent. So it turns out that these collections still satisfy the base exchange axiom, but it cannot be realized as actual vectors because it will break the purpose theorem. Right? So this is not representable over any field as vectors, although it turns out that it is representable as an algebraic matrix. Okay? So but there exists matrices that are not algebraic either. There's something called Mosh matrix, so maybe I'll leave it to you to look it up. Actually, I can draw it really quickly. So yeah. So let's see. So Mosh matrix is very hard to draw, but right here it is a matrix on 1, 2, 3, 4, 5, 6, 7, 8 elements, and then these 4 are coplanar. These 4 are coplanar. That means so this is a matrix of base rank 4. Rank is the size. Rank is the size of the each basis element. Right. So these 4 do not form a basis. These 4 do not form a basis. These 4 do not form a basis. Right. So if you're thinking of these are actual points in 3D, right? If you try to do this construction, you will see that these 2 points up here and these 2 points down here, they also have to be coplanar as well. Yeah.
So when you say that a Matroid is non-algebraic or is not a vector Matroid, what you're saying is that the particular dependency that you're establishing between the numbers in the size from 1 to n can be described as an algebraic relation of that type?
It cannot be, that's right.
That cannot be.
It cannot be, yeah, that's right. Yeah, so if it is not algebraic, means that I cannot find, right? I cannot find such a field extension, and I cannot find such element so that my independence come from algebraic independence.
So when you say that, for example, it is not representable over a certain field, you're saying there cannot be established an algebraic relation of that type over that field that allows you to create this matroid.
Yes, that's right. Yeah, so I can be even more precise than that. Yeah, that's right. So I cannot represent them as vectors. So what I'm saying right here, what I'm saying is, U24 is not representable over F2, meaning that I cannot find, right, 4 vectors in F2 squared, because this 2 is the rank, right? So I cannot find 4 vectors that I can put a column vectors, so that every 2 of them is linearly independent, right? So for the final matrix, it's not representable over real numbers, for example, right? So what I'm saying is a final matrix. This is a 7 elements, right, of rank 3. So what I'm saying is that there does not exist a 3x7 matrix over a field of characteristic not 2, such that, yeah, maybe if I label them, the vanishing of the determinant, the linear independence and non-independences coincide with my picture. Yeah.
For question, if I know that a matroid is algebraic over a field of characteristic K, does that mean it is algebraically representable over every algebraic closure of that field K? Or only like can I write it over in every algebraic closure or only in specific one?
Okay, let me see. I think you can take algebraic closures. Yeah. Maybe we can talk more about it. Yeah, I think yeah, taking algebraic closure doesn't change. Yeah, so this matrix representability reduced to whether checking a system of equations and inequality have a solution over that field. Yeah, do you have a question?
Yeah, so when you wrote U24,
Yeah.
would it be U42 if we're choosing 4 elements from the set, like 1, 2?
So I guess my notation right here, this is the basis of all the R element subsets of an N element set. So U24, my bases are 2 element subsets of a 4 element set. Okay. Yeah. Because convention, maybe some people use it the other way, I'm not sure. Yeah.
So did you actually prove that the Banus matrix is not?
I'm not gonna prove that.
Yeah, like, okay, how do you show that something is not algebraic? That seems very hard.
Yeah, that's right. So it is more of a case by case, really looking deep into it, yeah. Yeah, so this was shown in, I think, maybe in the 70s, and the title of the paper says non-algebraic matrices exist. Yeah. All right, so, okay, now let's also go back to a little more combinatorics, or maybe let me just make a comment, because now that we're talking about equations and inequations, so, right, checking representability is about checking whether a system of polynomial equations and inequalities, right, inequality because we want some determinants to be non-zero, right? Equalities have a solution or not, right? So you may say that, well, maybe this kind of systems is easy to solve. We know that in general, polynomial equations, they're kind of hard to solve, right? Maybe these are very special, maybe they're easy, but it turns out that they're not easy. There is something called Nioff universality. Basically, it says that these type of equations and inequalities are as hard as anything else. So in particular, over rational numbers, right? It is in general, we don't know. We don't know if it is decidable to see whether some equations have a solutions over rational numbers. So that means that it's also we don't know whether it is decidable whether a given matrix is representable over rational numbers. Okay, so there is a huge amount of difficult problems in the representability. So we're going to move on to easier things. Let's go to graphic matrices. So if you have a graph, let's say that G is a vertex set and edge set to be a graph connected to. And I'm going to label the edges with numbers 1 through n. So suppose that there are n edges. And then I'm going to let basis of my matrix to be edge sets of spanning trees. So T in the edge such that T is a spanning tree. So in other words, these are, right, there are n, so this is the same as, same as number of vertices minus 1 edges without cycles that do not contain cycles. Okay, so some more matrix terminology. So we said that in the script B's, elements are called bases. Sorry, I did not write that down. So these are called bases. Right, so script B is a collection of bases. And elements in a base or basis are called independent set, like imagine linear independence. And the things that are not independent are called dependent. And then elements that are subsets that are minimally dependent, they are called circuits, which follows from graph theory language as well. Right? Minimally dependent ones are cycles. Right. So let's do run an example right here. So let me do a 5. And then what are the bases? The bases are in this case, all there are 4 vertices. So all the collections of 3 edges that do not form a cycle, right? So I'm going to take all the element and you throw away the cycles 1, 2, 4 and 1, 2, 4 and 2, 3, 5. Okay, so we're gonna see this again. So I'm gonna actually write this down. Just gonna brute force write this down. 1, 2, 3, 2, 5, 4, 5, 4, 5, 4, 4, 5. Right, so there are 8 basis elements. And the independent sets are the ones without cycles, so they're forests. So this is called a graphic matrix. And it turns out that there is another matrix you can associate to a matrix called co-graphic matrix. So for that, I may introduce matrix duality. Yeah, let's say that I have a matrix and to be a matrix of rank R on an element set. And then the dual matrix M star is a matrix on the same ground set where the bases are given by complements of bases. And so these are complement. This is the letter B. This is, yes, this is the dual. So co-graphic matrix are dual of graphic matrix, and let's see what we get when we do it. To do this example. So here we have co-graphic. Right. So in this case, bases of the co-graphic are you take these bases and you just take complement for each of them, right? So 1, 2, 3 becomes 4, 5, 3, 4, and so on, 2, 5, 2, 4. And then I guess the names is suggesting that, this is a duality. So we know some kind of a graph duality, right? At least for the planar graph. So you take the planar graph and then you put a vertex for each of the regions. So right here we have the outside region and then 2 regions like that. So I can draw the dual graph in this case because this is a planar graph. So we have this other dual graph where I'm going to label the edges the same way, right? This edge is 2, I have 1 and 4 here, and 3 and 5 here, right? And you can check that the bases here are spanning trees in my dual graph, right? So matrix duality. But in general, if you take a non-planar graph, you still get a matrix, right? The co-graphic matrix is still a matrix, but it no longer comes from a graph. Okay, so in the space of all matrices, right? So I have, a graphic matrix and the co-graphic matrix. They're not the same thing, right? Duality switches between graphic and co-graphic. Graphic and. Okay, so duality. And then you're seeing that, it's an easy exercise to show that they're all representable, which I encourage you to try it out in the exercises. Okay, so they're all representable over every field. Yeah, so you can think of Matroid, doing Matroid theory as doing graph theory without talking about the vertices. And also with the advantage that now you have this nice duality theory. Which
You need to test membership.
is it easy to test membership in the graphic matrix? You know, if somebody knows, let me know. I have looked into it a little bit. I think it's not super easy. Easy as in like complexity, I guess. I mean, you can. I think there exist algorithms, but I don't think they are very efficient. I don't think it's like polynomial time. Yeah. I mean, it is decidable. Yeah, I mean, obviously, because there are only finitely many graphs, right? Also a number of edges, right? But yeah, I think people have done work on, trying to test the graph. Another tricky thing is like, it is not one-to-one. There can be two different graphs that give you the same matrix, right? Does anybody see what can I do to the graph that keeps it the same basis, for example?
Then another vertex.
Sorry?
Got a self loop and another vertex.
Oh, and a self loop and another vertex. Yeah, if you take a self loop like this, 6, and then you're changing the ground set though in that case.
Okay.
This kind of thing is called a co-loop. Right, so adding vertices, yeah, that doesn't, right? So that's why I put the word connected, right? So maybe less obvious thing to try is if you swap the label of 3 and 5, right? It keeps. So in general, if you have a cut of like 2 edge that would disconnect, I can cut it with the 2 edge and then I can flip it over and reattach. That gives you the same matrix. Right. Okay, now, yeah, I don't know how much time I have, maybe 20 more minutes? 30 more minutes, okay. All right, that's great. So now I will get to a question about matrix for negative dependence. So here's the questions about matrix. So suppose I choose 2 elements of the ground set. And then I pick in a matrix, right? And then in the matrix, pick a basis B among the bases uniformly at random. So let's compare the probabilities of having I in my randomly chosen basis, given knowing the J is already there versus not knowing anything about J. Right? Does anybody have a feeling on which one of these should be bigger? Right. Right? Think about a graph and a spanning tree. I already know, so my I and J are fixed, right? I already know that one of the edges is already in my basis, right? Does it make it more likely that my other thing is also in my base, or does it make it less likely my other thing is also in my base? Yeah, so is there inequality this way or that way? There's no right or wrong, right? So I don't expect you to like, immediately see it or anything, but what is your intuition saying? How many people think that is the first one? Yeah, how many people think it's the second one? Oh, interesting. Yeah, so most people said that it's the first one, it should be, right? So somehow the elements should sort of repel each other, right? You know that one is there, it's less likely the other one is there. We can check it for that example, for example, right? So let's do another example. Let's say I is equal to 1, J is equal to 2, right? Let's just check. So maybe let me rewrite this so that you make it easier to compute. So equivalently, I can write the probability of both I and j in my basis divided by probability of j in my basis less than or equal to probability of I in my basis. Right, maybe I can move this to the other side to make it look more symmetric. So check this. So if I have 1 and 2, so I'm choosing things out of 8 elements, so the denominator is going to be 8. Okay, and then both 1, 2, so I have 2 of them where 1 and 2 are together, right? So 2 out of 8 times that happens. And then probability that 1 is in it is 1, 2, 3, 4, and probability that 2 is in it is 1, 2, 3. Okay, so it is 4, 5, sorry. What is 5?
1, 4, 5 on the second one.
1, 4, 5. Ah, okay, so this is 5.
And the other one is 4.
The other one is 4. Okay, thanks. Okay, is this inequality hold? So, okay, we could cancel one of the 8. All right, and then, yeah, if I move it here, 16 less than or equal to 20, so it checks out. So is this always true? Okay, so that is the question. So we're going to approach this algebraically using generating polynomials. So the question is this true for all matrices or all graphs? Okay. Yeah, for algebraically, we're going to associate a polynomial to the matrix for basis generative polynomial. So this is going to be living in a ring over some field, I think over integers even, but let's say over R. Right, so we're living in where the variables are indexed by, let's see, indexed by elements in my ground set. Okay. And then the basis generating polynomial is you sum over all the bases, and for each basis you have a monomial. Okay, you have a monomial. Each basis is represented by a monomial. So in this example, this is going to be x1, x2, x3 plus x1, x2, x5 plus x1, x3, x4. Right, so this is for the basis generating polynomial. And we're talking about probability, so we're talking about uniformly choosing each basis element uniformly at random. So I'm going to put in a coefficient of 1 over the number of bases. But in general, we have probability generating function where you will sum over the same thing with the probability that the basis gets chosen. So you can talk about the same question with like different probability distribution. But right now for simplicity, I'm sticking to the uniform. But in general, you can say the probability of that basis get chosen times the same monomial. Right? In our case, this is going to be just 1 over the number of bases. And now let's try to rephrase these questions, the negative dependence, the thing at the top, in terms of this polynomial. So let's pause for a moment. How would I pick out maybe look at the right-hand side, maybe how would I pick out among these guys, how would I pick out all the bases that contains one? How would I throw away the ones that do not contain one? Like what operation can I do to the polynomial that will kill all the terms, right, without x1? Sorry? Evaluate?
Put some x equal to.
Yeah, so if we substitute, yeah, so maybe before I do this, right, if I substitute all ones, right, then I get one here, okay, yeah. Yeah, so, if you have a polynomial, if I want to kill, right, all the terms with x1, what operation can I do?
The derivative.
Take the derivative, right? You can take the derivative with respect to x1, that will kill all the ones with x1 in it, right? And then I can plug in 1. That will give me the probability that I is in B, right? And the same thing for J. So the question is, right? So the question becomes the probability that is whether I have probability of F, and then I plug in 1 to calculate the probability, right? Times how it compares to, right here, we need to do both x1, xi, and xj. Yeah. And then it doesn't hurt to put in of 1 here because this is just 1 anyway. So the negative dependence question becomes the question of whether this algebraic expression is true for the basis generated function. So it turns out that this kind of thing has shown up in the study of polynomials called stable polynomials, which I'm going to introduce now. Okay, so I'll give you the theorem first and then the definition. So this is the theorem of Rendon. So, all right. So Rendon says that a polynomial is stable, which I'm going to give you the definition in a moment, implies that, I'll set some notation first, actually. So, yeah, at the same time, okay, here's the notation, delta ij of f is defined to be this following expression. So I'll show with respect to xi times, I'll show with respect to xj minus f times second derivative. Okay, so this is again a polynomial. So f is a polynomial. Stable implies that this other polynomial takes non-negative value on Rn. It's a polynomial over R. Yeah. So in particular, if we can show that the basis generating function of our matrices and graphs are stable, then we will get the negative dependence. Okay, now I'll give you the definition of stable. So a polynomial with real coefficients is stable if I do a variable substitution and make it into a univariate polynomial. So here, for where A is a vector with positive coordinates and B is any vector, and the T is a variable. So if I look at this, if I do the substitution, this is a polynomial in a single variable T. So this polynomial is real root. Meaning all the roots are real. Okay, so let's unravel a little bit. Geometrically, what is happening? If I look at a polynomial, I can think of its vanishing locus. Suppose this is in my Rn. And then if I look at my vanishing locus of my polynomial, it has to look something like this. So this is like a picture of a stability. So if I have say degree 3 polynomials, and then if my hypersurface comes in these layers like this, and then this substitution is saying that I am poking my hypersurface with a line in positive direction, right? So if I poke it with a line in a positive direction, right? And in positive direction, right? I only made my hypersurface at real points, so I don't have imaginary points, right? So if my hypersurface is degree 3, I should be seeing 3 real points, so that there are no hidden complex thing that I'm not seeing, right? So the geometric picture that you should have in mind is that the stable polynomial, the hypersurfaces come in layers like this, right? So in the direction of the positive orthant. Okay, so in this layer, right, one of these regions is sort of pointing in the positive orthant. Right, so shifting around doesn't really matter, right? The positive direction matters. Okay. Yeah. So that's another way. So you can think of this as a multivariate generalization of being real-rooted, having real roots. So here's another equivalent characterization that you're going to think about in exercises. If you look at all the complex vectors, that is a root of the polynomial, means that the imaginary part does not lie, imaginary parts are not all positive. Okay? So if it is just a univariate, if n is equal to 1, univariate, then if it doesn't have, if the root cannot have positive imaginary part, then it cannot have negative imaginary part either, right? Because they come in complex conjugate pair. So you can see that for univariate, this is equivalent. Right? And then so this is for multivariate, it has this funny condition about imaginary part not being all positive. Okay, so it can be shown that these are equivalent definitions. So I think the word stability actually comes from PDE, stability of PDEs. So let's look at some exercises. Some examples. So if I have just a product of variables, it is stable. Right? You can also imagine geometrically, right? These are just coordinate hyperplane. So if I poke it in the positive direction, we go through all the hyperplanes at real points, right? Stable. Algebraically, you can also check that, if I just substitute, right? If I just substitute TA plus B into my x's, I get univariate polynomial, right? So f of TA plus B is TA1 plus B1. TA2 plus B2 and so on. Right. And then this univariate polynomial is real rooted. Yeah, the roots are right, negative BI or AIs. And so another nice operation that you can do if f is stable and a is in the positive direction, then the directional derivative is also stable. So this is easiest to see from the geometric picture. So if you're taking directional derivative in direction A, Okay, so you're restricting yourself to this line, and this comes from the fact that a polynomial is derivative interlace. So this comes from the fact that a polynomial, a real rooted polynomial, and its derivative in univariate cases, derivative, they interlace. Yeah, so in terms of picture, if you have a real rooted polynomial, so we have polynomial where all the roots are real, right? And then if you look at the derivatives, right, by Rolle's theorem, between every two roots, there's a root of the derivative, okay? So that means that the derivative also have enough real roots, okay? And then this is true in the positive directions. Right, so this already gave us some very nice examples. We know that the product, where is it? Product of variables is stable. Its derivatives are stable. So we could take derivative in, say if I take derivative in all one directions, all one direction of the x1 through xn, I get elementary symmetric polynomials. Okay, so this is so I take out x1 first, right, and then I take out x2, right, and so this is all elementary symmetric polynomial, n minus 1. Right, and then if you keep doing it, you get all the elementary symmetric polynomials, they're all stable.
Sorry, where are you taking the derivative of there in that example?
Derivative, sorry, this is the product. Okay, not the comma, thank you. Yeah, this is the product of variables. This monomial, right? And then I get these monomials, and then if I keep doing that, then yeah, I get all the elementary symmetric polynomials. Now, I don't have too much time, but I'm going to end with the result that the basis generating function or probability generating functions of graphic matrices are stable. Okay, so this will imply the negative dependencies for the graphic matrix. So what should I erase? Yeah. So before that, I think people who have seen this know that one way to get the basis generating function is there's something called matrix tree theorem. So matrix tree theorem comes from a determinant. So here's an important proposition that shows that how determinants give you stable polynomials. So we have a1 through an being d by d real symmetric positive semi-definite. And A0 is any symmetric matrix. Then let F be the determinant of the x1 a1 plus xn an plus a0. So you can think of, right, this thing in the parentheses, this is a symmetric polynomial whose entries are linear, right, affine linear polynomials in the axis. Okay. And then the coefficients are positive semi-definite. So quickly remind you, positive semi-definite, real symmetric positive semi-definite means that all the eigenvalues are non-negative, and equivalently, all the principal minors are non-negative. And equivalently, if you have something positive semi-definite, yeah, maybe I'll just write it. So A is positive semi-definite, means that all eigenvalues are non-negative. It also means all principal minors. Principal minors means that if you take some rows and then some columns in a symmetric way, the determinant is non-negative. Equivalently, if I do x transpose ax is bigger than or equal to 0 for all the vectors, x and Rn. right? So if you look at the corresponding quadratic form, it is non-negative. Also, it factors, as I can write A as this is, we're about to use this in the proof. A is equal to, check my notation. A is equal to U times U transpose for some matrix U. So let me give a quick proof of this because this is important. Any questions about the statement? Yeah, so this is, you can ask, well, okay, do all stable polynomials arise this way? The answer is no in general. It is true for a small degree, but not in general. So it is, a lot of people have looked into, trying to determine how can you decide, whether a polynomial is stable. If it is stable, does it come from determinant, and how can you find such a determinant of representation and so on. It's a big amount of work there.
But the conclusion is that this polynomial is stable?
This is stable. Sorry, I didn't write it. Thank you. It is stable. Thank you. Yeah. Okay, so let's this. So to check stability from the definition, right? So I take A in Rn plus and B in Rn, and then let's look at the polynomial. So f of T plus B, what does it look like? So this is the determinant of T, right? And you look at this linear combination of my positive semi-definite matrices plus my B1, A1 plus Bn plus A0. So it looks like that. And from this third definition of the positive semi-definite matrices, you can see that the set of all PSD matrices form a convex cone, because each of these inequality gives you a linear condition on the entries of A, right? I can think of this as linear condition on the entries of A. So it is defined by the set of all PSD matrices is given by infinitely many linear inequalities. So that means it's a convex cone. So that means if I take a positive linear combination of PSD matrices, I get another PSD matrices, not PSD matrix. So this is the PSD matrix. Okay. And this is some symmetric matrix. I'm just going to denote it with AB. Right? This is symmetric. And this is PSD. I'm going to denote it with big A. I need some more space. In fact, so in the homework, you're going to show that the set of stable polynomials form a closed set. Right. So using that, so that means you can talk about taking limits, and we can assume that it's enough to show that it is stable, it's enough to assume. We only deal with the case when this polynomial, instead of PSD, it is actually positive definite. Means that all the eigenvalues are strictly positive, all the principal minors are strictly positive, right? Positive definite. And then in this case, in the factorization, the matrix U is invertible, right? So assuming that because using the fact the set of stable polynomials are closed, using that stable polynomials form a closed set. Topologically in Euclidean topology. Right, so okay, now this is positive definite, then I can factor as U times U transpose where U is invertible. Right. Now I can factor things out from my determinant, right? So now my polynomial becomes, right? I can factor out the U and U transpose. So I get this determinant of T I plus U transpose U minus T. So the point is I can multiply things when you transpose and makes things nice over here. So now looking at this, so this one, whatever this is a symmetry matrix. Okay. I have a symmetry matrix and T is just one variable, right? Does anyone recognize this polynomial? What does it remind you of? This is just symmetry matrix, right? So what is this? What are the roots of this polynomial? The eigenvalues, right? Or negative of eigenvalues, right? This is the characteristic polynomial, right? Of this symmetric matrix. We know from linear algebra, the symmetric matrices have real eigenvalues. Okay, so that means that this one has 3 roots. Because it is a characteristic polynomial of the symmetric matrix. All right, now this really nice proposition that gives you large number of stable polynomials, and we want to show that for graphs, the basis generated polynomials have the determinative form. So I'll just do it in an example. Okay, so this is the matrix tree theorem with an example. Yes, since we're out of time, and on exercise, there is a more precise and more general version of it. In exercise that I'm asking you to think about a proof. Right, so matrix tree theorem. Yeah, actually, I'll write a version of this. So this is a spanning tree generating function. Spanning tree T C T is equal to determinant of it's going to determinant that looks like this. It's going to look like sum over all the edges, XE, VE transpose, where VE is a vector, it is EI minus EJ. Living in the space of, well, maybe I will write it like this. And then how about this? I'll write it determinant of this matrix after deleting 1 row and 1 column. Okay, so this one after deleting a row and a column. Let's say the last row and last column. Then I'm going to do it in an example. It'll be more clear what I mean. So going back to this example. Okay. So what I'm going to do is the way I wrote it over there, you can also write it like this. I could write working in R4, 1, 2. So these are the vertices. These are the edges. Maybe I should give them different names. Let's say A, B, C, D. And the columns are the edges. And then my first edge is, right, A is between A and B. Okay, I'm just giving them some arbitrary ordering of the vertices. Okay, it doesn't really matter. So arbitrary ordering of the vertices, and I'm just giving them 1 minus 1 or minus 1 1. It doesn't matter because when you do this multiplication, it doesn't matter if you put in a negative sign. Right, and then 2 is between B and D. B and D. 3 is between B and C. 4 is between A and D. And 5 is between C and D. Okay, so you have this matrix. And then putting in the xi's, you can think of it as inserting a diagonal matrix here. This one. And then say I have this matrix, the same matrix, but transposed over here. So 0. This one. So this is just a transpose of this one, right? So if you don't have this one, so people might have seen this as the Laplacian matrix. Okay, so if you don't have the x1 through xn, right? So what you end up getting is, or if you plug in x1 through xn to be or 1, you end up getting a matrix. It's kind of like the adjacency matrix, right? I have a 1 if I and j are connected, and then on the diagonal, you have the degree, negative of the degree of the vertices. But if I put in the x1 through x5, it has like a little bit of a more information. So this is a 4x4 matrix where if I have rows and columns are indexed by the vertices. And then let's say between A and B, there is an edge, right? So this is x1, so I'm going to put x1 here, right? And then, or rather negative x1. And then right here I have x2, right? And then on the diagonal, this is x1 plus, this is a diagonal corresponding to this A. So I have x1 plus x4. x1 plus x1. Sorry, I'm running out of space. So I have this 4x4 matrix. And then you can see that this 4x4 matrix, what is the determinant of this 4x4 matrix? So I have my diagonals correspond to it's kind of like the degree. It's the sum of all the edges coming out of it. And then in the off diagonal, I have 1 or 0, depending on whether, not 1 and 0, sorry, either variable or 0, depending on whether there's an edge or not. Okay. So between A and D, right, I did something wrong.
AC should be 0.
This is 0. Okay. And AD, right? This is minus x4, right? Okay, you see that row sums are all 0, right? So that means the determinant is 0, okay? So, but if I delete a row and a column, right, I'm going to have this is a determinant of a 3x3 matrix, and the entries are linear. So I have a degree 3 polynomial. It turns out the degree 3 polynomial is the basis generating polynomial of this one. Okay, so this is the matrix tree theorem. So that is, I'm going to wrap up right here. So this, to recap, right? So this shows that for graphs, for graphic matrix, so for graph, the spanning tree generating polynomial has the determinantal representation. That means that it is stable. And by Brandain's results that I have erased, right? Stability implies that these inequalities for negative dependence. Okay? So, any questions?
I'm sorry, I missed the last matrix. Could you explain that again?
Okay, how do I get this matrix?
No, I understood that, but why is that matrix? I did miss that part.
What is the result or what you?
Yeah, I mean, why are we getting that matrix? I understood XCVE and VE transpose. That is the first.
That is this is the
Oh,
matrix.
that is the multiplication. Okay, sorry.
Yeah, it's a different way to write it. It's a different way to write it.
Okay.
Right, so in the exercises, you're going to like stare at this matrix, apply Cauchy-Binet, and prove the matrix tree theorem. Yeah. So, okay, there's some obvious questions that people can be asking. What are some, like, okay, we have done this for graphic matrix, right? How about the other matrix? Okay, do the basis generating polynomials form a stable polynomial, or are there negative dependence? Right, so the answers are going to be no, unfortunately. So in today's exercise, there is one example of a matroid that do not have negative dependence. So it turns out that this repellent thing, your intuition is correct for graph, but it's not true in general. So it's borrowed from Jones' paper. It's a matroid that you can check by hand. That is a positive dependence. And then, so next lecture, we're going to move on from stable polynomials to a bigger class of polynomials called Lorentzian polynomials, or strongly log-concave, completely log-concave polynomials that still have the nice properties. So that the generating polynomials of all matrices will satisfy those conditions. Although there exists, I should have mentioned the generating polynomial of Fano matrix is not stable. Even if you allow different probability distributions, it's still not stable. So yeah, although stability is very nice, it doesn't work for all matrices. It works for matrices. Also works for representable matrices over real numbers, but it doesn't work for all matrices. Right, okay, so